Okay, welcome back. This was the second homework on the chain rule. So we learned the chain rule, we did some practice on the chain rule, then we did the derivation of the derivative of exponential functions and logarithmic functions of other bases. This is what was known as logarithmic differentiation, but I don't think I used that term until the video, which you watched last weekend. And then we did some real logarithmic differentiation. This was now then just more problems on the chain rule. So the chain rule is important enough that you got to practice it a lot to get good at it. Here we are. These were all the problems, but the ones in green we went over already in class, so I'm not going to go over those again. 51, 85 we did. Here we are at 87. I need to differentiate ln of x over x squared plus 1. Well, okay, the idea here is that you first apply a log rule. Ln of x over x squared plus 1 is ln of x minus ln of x squared plus 1. And as long as you apply that log rule first, then this becomes a pretty easy problem. What is the derivative then? The derivative of ln x is 1 over x, and the derivative of ln of something is 1 over the something back inside for the derivative of the something, so I multiply by 2x. So that's actually just it with that problem. Some of these were very short. 92 is basically just the same thing, to be honest. This is really the natural log of, well, this whole thing's being raised to the 1/3. So this is x minus 2 over x plus 2 to the 1/3. And, okay, no one ever adds in more parentheses because it's sort of like ugly, but of course the understanding is that this is all inside the natural log. It's the natural log of that. Okay, well here I'm going to do two things. I'm going to apply the log rule that says that you can pop down that 1/3 to the front, and I'm also going to apply the log rule that breaks this up into a difference of two logarithms. In other words, prior to differentiating, I'm going to write this as 1/3 comes on the outside, and then the stuff that's left over becomes ln x minus 2 minus ln x plus 2. Cha cha cha. So I mean, this comes up so often that, you know, this is important to do a lot of practice. Well, okay, now we can differentiate. So what do we get? Well, we get 1/3 times the derivative of the natural log of x minus 2 is 1 over x minus 2 back inside for the derivative of x minus 2, which is just 1, minus the derivative of the natural log of x plus 2. Well, the derivative of the natural log of something is 1 over the something back inside for the derivative of the something, which is just 1. So this problem is also just over. Okay, 125. Maybe I want a little bit more space. Y equals 5 to the x minus 1. Sorry, y equals 5 to the x minus 2 is this number 125. Well, yeah, I mean, there's a couple different ways to do this. The most efficient way to do it is to just have previously proved / memorized the formula for the derivative of 5 to the something. What is the derivative of 5 to the something? I guess we did this so many times in class, maybe again on the video, again in class the second time. So maybe I don't need to reprove it, it's just that. Okay, well, if you have this fact just in your brain, or you're willing to derive it off to the side, then I can just go directly into this problem. By that I mean use the chain rule. What is dy dx, therefore? Well, the derivative of 5 to the something is ln 5 times 5 to the something. Back inside for the derivative of x minus 2, but the derivative of x minus 2 is just 1, so this problem is also just over. 126 was a lot harder. We did that one in class. Let's get to 135, which is over here. Well, this is, I think, also kind of easy, I guess. Y equals log base 5 of the square root of x squared minus 1. So, okay, let's see, what's the best way to do this? Well, first of all, maybe the very first thing to do is to just realize that, you know, this log base 5 thing is just not something I feel like dealing with. There's a change of base formula. Change of base formula says that the log base b of anything a is just ln a over ln b. So I can rewrite this as just 1 over 1 over natural log of 5, ln 5, times the natural log of root x squared minus 1. But of course, I can do even more because this is really like 2 to the 1/2, right? So maybe I'll just kind of do it now, right? This is x squared minus 1 to the 1/2, so I can also use the log rule to pull down that 1/2. So I end up with 1 over 2 ln 5 times the natural log of x squared minus 1, and sort of only now do I differentiate. And some people, you'll even see people like popping that back up. So just to write that, sometimes people don't like 2 ln 5. It could be sort of written more nicely as ln 25. I'm not sure exactly what the back of the book said here, but okay, if we differentiate this, what do we get? 1 over ln 25 times, finally I'm doing some calculus, what is the derivative of the natural log of x squared minus 1? The derivative of ln of something is 1 over the something back inside for the derivative of the something, and the derivative of x squared minus 1 is 2x. So, okay, let's see, I guess it's kind of like this going on here. So, right, final problem that I can fit on the board is this problem 145. It's very similar to the problem from the previous homework. They give you sort of partial information about about g and h at 5, and the goal is to compute the derivative of f at 5 for each of these 4 problems. So this is like sort of 4 separate problems really with the same little prompt. The prompt being, you know, given this information over here. Okay, so let's do it. Maybe I'll do it in purple. So here I'm going to use the product rule. So what happens is I take the derivative of f, and the product rule says that it's the derivative of the first times the second plus the first times the derivative of the second. And now I'm just going to plug in 5. So what is f prime of 5? Keeping this video kind of fast, I'll just go right to it. It's g prime of 5, which is 6, times h of 5, which is 3, plus g of 5, which is negative 3, times h prime of 5, which is negative 2. So I guess I get 18 and 6 is 24. Cool. Okay, how about C? Well, this is also just an old sort of thing, right? Now I can take the derivative and I will use the quotient rule. So it's the derivative of the top, g prime, derivative of the top times the bottom, minus the top times the derivative of the bottom, all over the bottom squared. Chop. So, okay, what is all this? Well, the derivative of, now I'm going to plug in 5. So, what is f prime of 5 specifically? Well, I'm just going to plug 5 into the general formula for the derivative of f. So, g prime of 5 is 6, h of 5 is 3, minus, it's really just the same thing, right? Well, it's not the same thing, but g of 5 is negative 3, and h prime of 5 is negative 2. It's the same sort of numbers as with the product rule, but there's a minus there instead. Okay, all over, what is h of 5? It's 3, so that's 3 squared down there. Okay, so what does this turn out to be? 18 minus 6 now is 12 over 9. So that is 4/3. Confidence in that answer, medium high. Let's see. Let me just double check that. 18 minus 6, it definitely is 12. 12 over 9 is definitely 4/3. So yeah, I guess we're good. Okay, but then there's like a trick built into this problem. Here's the trick. The problem actually says, you know, find f prime of 5 if possible. So, well, what does that mean? Well, here, if I go to differentiate f, what is f now? It's the composite of two functions. So this is the section on the chain rule after all. So they want to see if you understand the chain rule well enough in this sort of abstract kind of problems to have the confidence to, well, first I'm going to differentiate it, and what is the derivative of g of h of x? Answer, it's g prime of h of x back inside times h prime of x. And now I see I'm going to run out of room a little bit here. So, okay, looking good. Well, that's just the chain rule, of course. But now I want to know the derivative at 5 specifically. So if I want the derivative at 5, let me plug in 5 for x. Well, that's going to be g prime of, what is h of 5? H of 5 is 3. And what is h prime of 5? It's negative 2. But it's at this moment that I realize that I cannot complete this problem as written. It is not possible for me to go on because I don't know what g prime of 3 is. Notice that g prime of 3, I have no function, I have no general rule for this function, I have no graph, I only have this sort of 4 tiny pieces of information that were given in the problem, and I'm not given what g prime of 3 is. Okay, I think this problem is like sort of worth doing and worth talking about because it sort of highlights that in a certain sense that when you're doing the chain rule and you're interested in the rate of change of the outer function, you're interested in the rate of change of the outer function not at the place where we're differentiating, but at the place where the inner function is outputting. In other words, the big idea here is what's the derivative of f at 5? And it seems, if you don't understand what you're talking about at all, it seems like everything is happening at x equals 5. And indeed, it's how fast h is changing at 5 that seems to be mattering. That's the negative 2. But when it comes to seeing what g is doing, of course, when x is 5, h of x is 3. And so the information you need to sort of finish this problem is the rate at which g is changing at 3. Not the rate at which g is changing at 5. You need to know, the chain rule says you need to know how fast the outer function is changing near its own input. And the input to the outer function is the output of the inner function. And so it really is h of 5, which is 3, that all the action is happening. And so since I'm not given that information, then you're supposed to say not possible here. So okay, that was maybe kind of hard or something. But over here, this problem now I think we can do because this is also a chain rule problem, but the inner function is g and the outer function is like cubing. So what is the derivative of this function f? Well, the derivative of something cubed is 3 something squared back inside for the derivative of that something. And so if I specifically want the derivative at 5, I broke my color scheme here, oh well, then I just plug in 5 here, so this is going to be 3 times, what is g of 5? It's negative 3 squared, and g prime of 5 is 6. So the answer to this problem is 3 times 6 times 9, I guess. So what is that, 81 times 2? Is that right? 162, not sure if that's right at all. 9 times 3, 27 times 6. 120 and 42. Yep, did that problem 2 different ways. Okay, so that was 145. Okay, be back with a couple more in a second. Okay, back for the last two from section 3.4, which is 153, 154. The directions for both of these problems are the same. Directions are determine the points at which the graph has a horizontal tangent line. Specifically, we're doing this on the interval 0 to 2 pi. Okay, when does this function have a horizontal tangent line? This is like 10% calculus, 90% pre-calc, so let's go. I want to see when the derivative is 0. Let's take the derivative. Alright, easily done. What is the derivative of 2 cosine x? Well, the derivative of cosine x is negative sine x. So that's negative 2 sine x. What's the derivative of sine 2x? Well, the derivative of sine of something is cosine something back inside for the derivative of the something. Alright, so if you know the derivative of sine and cosine and you know the chain rule, like I just took the derivative and that took 10 seconds. But now the problem sort of really starts or something, because I want to know when this function has a horizontal tangent line, so therefore I need to set this thing equal to 0. And so we end up here, when is cosine 2x minus sine x equal to 0? I just divided both sides by 2. Okay, and now this is just a straight up pre-calc B problem, like being solved by pre-calc B students all across America. Can you just like solve this trig equation? I guess that we can. How do you do it? Well, you need to have on the tip of your fingers like all possible formulas, and in particular, cosine 2x is cosine squared x minus sine squared x. And that's just a math fact that you really just need to just know and just love and understand and just completely have it. Well, actually, I don't want this form of it. I want the form of it in which we replace cosine squared with 1 minus sine squared. And if you do that, you get 1 minus 2 sine squared x. You might also have that formula memorized. Well, if you have it memorized, that's good, but also you need to know that that's the right thing to do here, because doing that is strategically wise. Now I have converted everything into an equation involving just sines. Okay, so now this is quadratic in sine, so this can be rewritten as 2 sine squared x plus sine x minus 1 by multiplying through by a negative and rearranging terms. Finally, I'm going to factor. I hope it factors at least. I bet it just does, because like it looks like it factors. I'm about to find out. 2 sine squared x plus 2 sine x minus 1. Boom. Therefore, zero product property. This is going to be true when 2 sine x minus 1 is 0, or when sine x plus 1 is 0. Let's find those. Well, that's when sine x is 1/2, and that is when sine x is -1. So, going over here to the unit circle that you have sort of built in your brain, when is sine 1/2 on the interval from 0 to 2 pi? Boom, here, and when is sine -1 here? And so I guess the answer to this problem is x equals pi over 6, 5 pi over 6, and 3 pi over 2. At each of those x values, f has a horizontal tangent, because at each of those x values, the slope of the tangent line to the curve is 0. Okay, 154, exact same problem. How should we do this? You have some choices here. You can do the quotient rule, but here's the thing, I have to do the chain rule anyway. This is 2x minus 1 to the 1/2. So personally, okay, this is just my preference, but here's a situation where I would just write this as x times 2x minus 1 to the -1/2. In other words, I'm just going to use the product rule, and yeah, the sort of secret about the quotient rule is you don't ever, now that you know, I don't think I've said this yet in class, I might have said this in one period, now that you know the chain rule, you don't ever have to use the quotient rule ever again. If you give me some problem where any reasonable normal person would use the quotient rule, say like what's a kind of a classic problem? I don't know, x over sine x, let's say, and you want to differentiate that. Well, 95% of people would just use the quotient rule here. That's kind of what the quotient rule is good for, right? Let's make that x squared. So it would be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay, and that's probably the fastest way to do this problem. But if you want to be weird or whatever, you could write this as x squared times sine x to the -1. And then you could just use the product rule. So if you're going to do it that way, then you'd say it's the derivative of the first, which is 2x, times the second, so times sine x to the -1, plus the first, times the derivative of sine x to the -1, which requires the chain rule. What is the derivative of something to the -1? Answer, -1 thing to the -2 back inside for the derivative of sine, which is cosine. Is this easier? It probably isn't. But does it avoid using the quotient rule? Yeah, it does. And maybe that's the kind of person you are. If you get a common denominator over here on the right, you will see that it's the same thing as you get from using the quotient rule. So the quotient rule is sort of technically obsolete once you know the chain rule. So just maybe be aware of that. All right, sorry, I don't want to waste too much more time. I'm going to erase this. So this is a situation where it just seems easier to use the product rule. So I'm going to just do that. What do I get? I get derivative of... Sorry, I made a mistake and had to do some edits. Sorry about the continuity error. Anyway, here we go. I think this is going to be faster to do it this way, like I was just saying, I think. So let's go. Ready to differentiate using the product rule. Well, what do we get? We get kind of continuity error here. We get the derivative of the first, which is 1, times the second. So that's 2x minus 1 to the negative 1/2 plus the first x times the derivative of the second. What is the derivative of 2x minus 1 to the negative 1/2? Here we need to be careful. What is the derivative of something to the negative 1/2? Answer, negative 1/2 something to the negative 3/2 back inside for the derivative of 2x minus 1, which is 2. Okay, so I'll just say that one more time. Derivative of the first, which is 1, times the second, plus the first, x, times the derivative of the second. And the derivative of 2x minus 1 to the negative 1/2 requires the chain rule. The derivative of something to the negative 1/2 is negative 1/2 thing to the negative 3/2 back inside for the derivative of 2x minus 1, which is 2. Okay, so what do I get here? I get 2x minus 1 to the negative 1/2. The 2 cancels the 1/2, so that becomes minus x, 2x minus 1 to the negative 3/2. Okay, and now there's sort of like a move or something to do here. I want to know when this derivative is 0. And if all you care about is when the derivative is 0, by the way, that is all we care about, you might think, okay, can I just like set this equal to 0 as fast as possible and solve? Yeah, you could, but a better method is to just kind of simplify this derivative a little bit in a way that kind of preserves it. And so, all right, what I need to do here is like factor. How do I factor this? It's not totally obvious how to factor this, but what I want to do is take out a 2x minus 1 to the negative 3/2. Why do I want to do that? Well, it's just something I've sort of observed about factoring, which is that if you give me two things like a squared plus a to the 7th and you ask me to factor it, well, what am I going to do? I'm going to factor out an a squared, leaving me with 1 plus a to the 5th, and everything looks wonderful. Okay, in other words, I'm going to factor out the smaller of the two numbers. Could you have factored out a to the 7th instead? Well, I guess you could. That would give you a to the 7th times a to the negative 5th plus 1. And while that's not wrong, it's not really what I want because I have now created negative exponents in my life, which I don't want. Therefore, moral of the story, this is basically like algebra 1 here or something. The moral of the story is whenever you have two things that you want to factor with different powers, you should take out the lower of the two. And that applies to negative numbers as well. So, faced with two terms that both have 2x minus 1 to the somethings in them, I'm going to look at those exponents, see that to the negative 3/2 is lower, and factor that out. So now I'm left with 2x minus 1, like to the 1, right? Because something to the negative 3/2 times something to the 1 is something to the negative 1/2. Okay, and then minus x. Alright, so what have I done? I've just done a little bit of algebra, and suddenly my problem now is like so easy and simple and beautiful. What do I get? 2x minus x, so I just get x minus 1 over 2x minus 1 to the 3/2. So that is sort of worth doing in my opinion because I now have an expression for the derivative, but that expression is extremely simple. And what was my goal again? My goal is to find out when there's a horizontal tangent line. That's going to be when the derivative is 0. So of course by inspection, the derivative will be 0 at 1. So f prime of 1 is 0, so f has a horizontal tangent at x equals 1. Okay, good. Let me be back in a minute for the last 3 problems. Okay, last 3 problems. Here we go. This is from section 3.5, which we haven't really done yet, but this introduces implicit differentiation. Well, I haven't used that word even in class yet. This uses logarithmic differentiation. Here's a problem number 67. Task is find the derivative. Well, you could just do it, right? What is this? It's a quotient. Inside the denominator is a composite of 2 functions. In the numerator is a product of 2 functions, and here we even have a composite. So this is a composite of 2 functions inside of a product rule, inside of a quotient rule. So there's going to be just sort of a lot of kind of recursive applications of the product rule and quotient rule and chain rule. So that's fine, you could do that, or it's faster to just take the natural log of both sides. This is what we did in the video over the weekend. So I do that right now. I take the natural log of both sides. And what is this? It's x squared times, of course this is just 3x minus 2 to the 1/2. I'm doing some rewriting kind of as I go. X minus 1 squared. And now, what? Now I apply log rules. So maybe this time I'll write everything out. This is ln of x squared times 3x minus 2 to the 1/2 minus ln of x minus 1 squared. So in other words, I just applied the log rule that says the log of a quotient is the difference of the logs, right? Ln a over b is ln a minus ln b. But of course I can keep going, right? Because here I can do the log of a product. So that's ln of x squared plus ln of 3x minus 2 to the 1/2 minus ln x minus 1 squared. And now I can apply 3 times the other log rule that says that you can bring things down. So this becomes 2 ln x plus 1/2 ln 3x minus 2 minus 2 ln x minus 1. And now just like so much headache has been avoided. Now I differentiate both sides with respect to x. What is the derivative of ln y with respect to x? Well, the derivative of ln y, the derivative of ln of something is 1 over the something back inside for the derivative of the something. And on the right-hand side, because my function has been split into tiny little pieces, it becomes really easy to differentiate. What's the derivative of ln x? It's 2 times 1 over x. Here we get, oh man, kids downstairs. What's the derivative of ln of 3x minus 2? 1 over 3x minus 2 back inside for the derivative of 3x minus 2, which is 3, minus 2 times, and the derivative of ln x minus 1, derivative of ln of something is 1 over the something back inside for the derivative of x minus 1, which is 1. So, what is dy dx? Answer, oh man, they're so loud down there. Dy dx is y, so that's x squared root 3x minus 2 over x minus 1 squared, times 2 over x plus 3 over 2 3x minus 2, minus 2 over x minus 1. Okay, that still took like 5 minutes, but I think it's much easier than doing it just in a straightforward manner without doing logarithmic differentiation. Okay, let's do these last 2 problems. 71. 71 is x to the 2 over x. Y equals x to the 2 over x. Okay, well, here you have both the base. Here you have a function that we're trying to differentiate in which both the base and the exponent are growing. And the only way to do this is with logarithmic differentiation. So this is logarithmic differentiation optional. This is logarithmic differentiation obligatory. In other words, I am forced to take the natural log of both sides in order to be able to bring down that, that function that's up in the exponent. Okay, well, we do it. What do we get? ln y equals, bringing that down, 2 over x times ln x. And yeah, I mean, now I suppose I'm just going to take the derivative of both sides. So let's take the derivative of ln y, and on the right hand side I'm going to take the derivative of, it seems easier to me to write this as 2x to the negative 1 times ln x. Sure. Okay, so what is the derivative of ln y? Okay, after doing this over and over again, hopefully it's becoming more reasonable. The derivative with respect to x of ln of y is 1 over y back inside for the derivative of y, which is dy dx. And now on the right hand side I have to do the product rule. The derivative of the first is going to be negative 2x to the negative 2 times the second plus the first 2x to the negative 1 times the derivative of the second. And the derivative of ln x is 1 over x. And so actually, in fact, this works out kind of nicely over here. What do we get? Well, we have dy dx equals, I multiply both sides by y, and then what is all this stuff? Well, I get, in fact, I get negative 2 ln x over x squared, but this is just like plus 2 over x squared as well. Because x to the negative 1 divided by x is x to the negative 2. Okay, and so my final answer, dy dx, is in fact just the original thing, y, so that's x to the 2 over x, times 2 minus 2 ln x over x squared. And, okay, personally I would just leave it like that. It's possible to be even more efficient or something, and write this as x to the 2 over x minus 2. Potentially you could do that if you find that to be like nicer or something. So that's an alternative way of writing that final answer. Okay, I feel like we got this under control now, but you know, with practice and repetition comes mastery. So what do we have now? We got one more problem that's really the exact same thing. In fact, it's even easier. X minus 2 to the x plus 1. Okay, let's go. How do I differentiate you? X minus 2 to the x plus 1. Well, answer with logarithmic differentiation. So take the natural log of both sides. So ln y equals, and here I'm just going to be cool and just do it all at once, right? Because the ln of all of this, then that's going to pop down. So hopefully I don't lose people by just taking the log of the right-hand side and applying the log rule simultaneously. And now I differentiate both sides with respect to x. The derivative of ln y is 1 over y back inside dy dx. And now for this I use the product rule, so derivative of the first times the second, so that's ln x minus 2, plus the first, x plus 1, times the derivative of the second. What is the derivative of ln x minus 2? It's 1 over x minus 2, back inside for the derivative of x minus 2, which is 1. Therefore, dy dx is y, otherwise known as x minus 2 to the x plus 1, times ln x minus 2 plus x plus 1 over x minus 2. And that is it for this homework on the chain rule. Goodbye.